dimensional gauge theory that's called n equals 4 super Young mills with the gauge group G, which will be a compact simple Lie group, or its Langlands Goddard-Neutz-Olive dual group, G dual. So the theory based on G has what's called a coupling constant E and a topological angle theta. They combine to a complex parameter with a positive imaginary part. And there's an elementary symmetry that shifts tau by 1 because instanton number is integer valued. There's also a dual theory based on the dual group. It has an analogous dual parameter, also with an elementary symmetry. But the duality that leads to geometric Langlands is a non-elementary symmetry. The assertion is that the theories based on a group and the dual group are equivalent under this change of variables that inverts the coupling constant, where n sub g is 1 for simply laced g and otherwise is 2 or 3. Now, this isn't a statement about geometric Langlands particularly, and it's studied in many different directions by physicists interested in questions that are not closely related to geometric Langlands. But we can specialize to a situation that does lead to geometric Langlands. First, we consider what's called a topological twist that leads to a family of topological field theories parameterized by CP1. They're parameterized, let's say, by complex parameters, psi or psi dual for the group or the dual group. So if we study the whole family, then, well, we can have these elementary symmetries, but we have a non-elementary equivalence that relates the group to the dual group. And the whole collection of dualities becomes the duality of what's called quantum geometric Langlands. But today we'll consider the basic geometric Langlands duality between the case that psi equals 0 for the group G and psi dual equals infinity for the dual group. So I'll call these the A model and the B model because they have a close analogy with the A model and the B model familiar in mirror symmetry. And well, I'll even explain a version of that analogy in a moment. Now, in general, quantum field theory in dimension D associates a number of the partition function to a D manifold, a vector space, the space of physical states, to a D minus 1 manifold, and a category of boundary conditions to what a D minus 2 manifold. That's a misprint there. So in the present context, though, we won't study an arbitrary 4 manifold. We're going to look at 4 manifolds of the form sigma times C, where we keep C fixed and only let sigma vary. So C will be the 2 manifold that's studied in geometric Langlands. Sigma will be completely arbitrary. So in effect, we'll study a 2-dimensional theory that depends on the choice of C. So that means since C is kept fixed, what we're varying is only a 2 manifold. So effectively, we're going to be viewing a 4-dimensional topological field theory as a 2-dimensional topological field theory. So the category we get will depend on C. Now, it's convenient to draw 2-dimensional pictures in which we only exhibit sigma and not C. And I'll draw such pictures. So here's a picture where I show sigma as having a boundary. So the shaded area is the 2-manifold sigma. It has a boundary, which is the black line on the left. And to formulate quantum field theory on sigma, we need a boundary condition. And boundary conditions make a category. Given 2 boundary conditions, B1 and B2, Hom from B1 to B2 is the vector space that the quantum field theory assigns to this picture, where I've given sigma a boundary on both sides. So now, sigma, in my picture, sigma is oriented. The arrows are keeping track of the induced orientation of the boundary. The plane is oriented in which sigma is embedded. So this picture, the corresponding physical state space in category language is Hom from B1 to B2. I should warn you that physicists don't usually use this terminology, except in particular areas where it's useful. So with this definition, Hom from B to B is an algebra for every B. In this picture, I didn't label the boundaries, but they would all be labeled, for example, by the same boundary condition B. So the open string propagating in time represents an element of Hom from B to B, but we've joined 2 of them to make 1. And that gives a composition law from hum BB to times itself to hum BB. And by drawing another picture with three of them joining, you would show that this is an associative multiplication. And moreover, by similar pictures, but now labeling the boundaries not all the same way, but different ways, you learn, for example, that hum from B to B prime is a left module for hum from B prime to B prime, and so on. So I know on YouTube you can find videos explaining that the axioms of category theory can be captured by two-dimensional pictures like I'm drawing. I'm not giving a complete explanation, I'm just drawing some of those pictures. So electromagnetic duality will give an isomorphism between a category curly C associated to a two-manifold C in the G theory at psi equals 0, and a dual category associated to C in the dual theory at psi dual equals infinity. Now, in addition, there's a natural mapping between certain natural functors on C and C dual. So these functors come from what physicists call line operators. So in a quantum field theory defined on a manifold M, a line operator in general is some sort of modification of the definition of the theory along an embedded one manifold K. So the natural line operators at psi equals infinity are what physicists call Wilson operators, related to the holonomy of a connection. And the natural line operators at 0 are what physicists call 't Hooft operators. So in physics, these operators are usually studied to analyze questions like quark confinement in atomic nuclei and other questions about universality classes of quantum field theory. But for us today, a line operator is a functor from the category of boundary conditions to itself. And we can understand that statement from these pictures. So what I've shown in part A, so the boundary has been labeled by B, but I've drawn a line operator that runs along the boundary. In topological field theory, there's no notion of how far apart they are. So you could think of this line operator T as arbitrarily close to the boundary, and they simply make a new composite boundary condition, T times B. So a line operator T gives a mapping at the level of objects from object B in the category to a new object TB. But we also would like to know what it does to morphisms in the category. So a morphism can be represented as a junction between two different objects labeling different regions of the boundary. So here, unfortunately, I've compressed a few pictures into one, but forget the T for a moment. The boundary has been labeled piecewise by three different segments, B, B prime, and B double prime. Three parts of the boundary are labeled by three different boundary conditions. And the junctions between those boundary conditions are morphisms in the category. And this picture is supposed to represent the idea that T acts not just on objects, but on morphisms between objects in a way that satisfies the axioms of category theory. I really needed more pictures to more fully explain this. One picture I really needed, though, was to explain the relation between this kind of picture, where objects are represented by a strip coming in, morphisms. Here, a morphism between two objects in the category I represented, or in this picture, as a strip with two different boundaries labeled by different boundary conditions. Here, the strip has been conformally mapped to a point. Well, a picture with a strip coming in has been conformally mapped to this picture. So I needed a few more pictures to explain all this more systematically, but I hope I've said enough to orient you at least. Now, I've been drawing pictures in 2 dimensions, but there are 2 more dimensions not drawn because there's a 2-manifold C that's being kept fixed in this discussion. And the line operator T really depends on the choice of a point in C. Well, we're specializing to the case that the line operator is supported on a 1-manifold in sigma times a point in C. We could study more general 1-manifolds, but for today we're specializing to that case. So therefore I can draw the support of T as a line in the 2-dimensional picture, but it lives somewhere inside the 2 manifolds, 2 dimensions that aren't drawn. Now such pictures make it obvious that the line operators T of P and T of P prime commute. In a purely two-dimensional picture, it looks like we'd have trouble moving this line to the left of this one. We might meet a singularity. But in 4 dimensions, it's obvious there's no singularity. The picture describes first acting with T of P on sigma to make T of P times B, and then acting with T of P prime on the composite to make this. And from the point of view of two-dimensional pictures, the T of P and T of P prime might not commute. But in 4 dimensions, it's obvious that we can move P past P prime with no singularity because these two lines are really supported at different points in C. So it follows that the functors associated to these line operators commute. So the two dual categories are equipped with dual families, T of P and W of P, of functors parameterized by the choice of a point in C and some other data, and commuting at distinct points. So T of P corresponds to the usual Hecke functors of geometric Langlands, and the duals which are W of P are dual in the usual geometric Langlands duality. These functors actually depend on more data, namely a representation of the dual group. So you can also consider compositions at the same point P of operators associated to different representations of the dual group. And they again commute, but a little less obviously. The duality says that the algebra of compositions of the Hecke operators should match the algebra of composition of the Wilson operators, which on elementary grounds is the tensor product of representations of the dual group. The fact that they do match is known mathematically, or at least in the context of geometric Langlands, it's called the geometric Satake correspondence. For physicists, it's the duality between the operator product expansion of 't Hooft and Wilson line operators. Now, to go into a little more detail, I want to introduce a useful language for a simplified version of geometric Langlands duality. So, the moduli space of G Higgs bundles on a curve C is what I'll call M sub Higgs of G and C. Well, H is Higgs or Hitchin, as you wish, or just MH of G if C is understood. As shown by Hitchin, this is a hyperkähler manifold. In one complex structure, it parameterizes Higgs bundles. In another complex structure, it parameterizes flat bundles over C. So the two complex structures and their product act as the unit quaternions, making a hyperkähler structure. There also are the 3 corresponding Kähler forms. So geometric Langlands duality can be understood for many purposes as a mirror symmetry between the Higgs bundle moduli space of G and the Higgs bundle moduli space of the dual group. More specifically, it's a mirror symmetry between the A model of the Higgs bundle moduli space in one of its symplectic structures and the B model in one of its complex structures. This instance of mirror symmetry is particularly simple because it's a rare case where the Strominger-Yale-Zaslow interpretation of mirror symmetry can be made rather explicit. And it was first studied mathematically by Hazel and Thaddeus. Now, you can definitely ask questions for which the two-dimensional picture is inadequate. Mathematicians describe this by saying that the theory has to be formulated not on a finite dimensional moduli space, but on the stack of all G bundles, bun G. Physicists describe the same thing by saying that the correct formulation is a duality of 4-dimensional theories, not 2-dimensional theories. 4 is the minimum. There's actually a 6-dimensional formulation that explains some things better, but 4 will be enough for today. The two descriptions are not so different because Atiyah and Bott showed in 1981 that a model of bun G is the space of all connections on a fixed smooth G bundle over C. So 4-dimensional gauge theory is a 2-dimensional theory with target bun G. That's actually, I would say, the translation between the way mathematicians and physicists deal with this assertion. Now, I want to use the 2-dimensional description of geometric Langlands duality as mirror symmetry to explain why the category that appears on what mathematicians call the automorphic side of the duality, which is this one, is the category of D modules on bun G. So remember, on this side of the duality, we have an A model. So I have to explain why the A model, or mathematically the Fukaya category, is related to D modules. So the most familiar branes or objects in the A model are Lagrangian branes, which are supported on a real Lagrangian submanifold. But Poisson and Orlov discovered that in general one can define what they called coisotropic A branes that are supported on a coisotropic submanifold that's above the middle dimension. These are extremely fascinating and not so much studied things. And their construction is delicate in general, but the simplest case is the case we actually need here. The simplest case is that Y is actually a complex symplectic manifold with complex symplectic structure I and a holomorphic symplectic structure that I'll write this way. The notation is adapted to the hyperkähler case, where there are 3 symplectic forms, but at the moment, omega J and omega K are just names for the real and imaginary parts of capital omega. So we view Y as a real symplectic manifold with M omega as the symplectic form. And we take what's called the B field of the 2-dimensional theory to be omega J. So this is not exactly how Poisson and I did it originally. We used a variant that differed by what's called a B field gauge transformation. But anyway, in this setup where you have a real symplectic manifold that you have a complex symplectic manifold, you take the imaginary part of the symplectic form to view it as a real symplectic manifold, and you take the real part of the holomorphic symplectic form as a B field. That's the simplest case where you can construct what Poisson and I called a canonical coisotropic A brane. But it had been discussed earlier by Poisson and Orlov. It has the property that roughly Hom from BCC to itself is related to deformation quantization of the algebra of holomorphic functions on Y. So the existence of this brane is an explanation of why the A model of a complex symplectic manifold viewed as a real one is related to deformation quantization. Now, what we need here is a simple or special case of that statement. If the complex symplectic manifold Y is actually a cotangent bundle with the standard complex symplectic structure, then you can show in more detail that Hom from BCC to itself is the sheaf of holomorphic differential operators on the base, twisted by the square root of the canonical bundle. So anyway, without getting into too much detail, in this situation, by considering this particular rather exotic object in the A model, you find differential operators on the base W. So in the case of geometric Langlands, we take Y to be the Higgs bundle moduli space, which according to Hitchin is birational to the cotangent bundle of the moduli space of holomorphic G bundles on C. So A, which is Hom from BCC to itself, is the sheaf of holomorphic differential operators on the moduli space of bundles. Now, if B is any other brane, then Hom from B to BCC is going to be a module for A, which is Hom from BCC to itself. In other words, the category of, on the automorphic side of the geometric Langlands duality, will be a category of, roughly speaking, D modules on M of G. Now, mathematically, it's important to work with D modules on the stack bun G, not on a finite dimensional moduli space. Physically, what that means is that it's important that a version of the coisotropic brane can be defined directly in 4 dimensions, not only after reducing to 2 dimensions. Poisson and I had a version of that in our original paper, but Gaiotto and I improved it a few years later. And by improving it, we were able to give an answer in the physics approach to a question that had been unclear to me and will be important later in this lecture. So there's this special A brane that's related to D module, to differential operators on the moduli space. But what is its dual? So BCC is an A brane on the moduli space for G, so its dual will be a B brane of the dual group. In other words, a coherent sheaf on the moduli space of the dual group. To be more exact, what's the right sheaf was clear mathematically from the work of Beilinson and Drinfeld. The dual of BCC is, according to their work, is the structure sheaf of the variety of O pairs, which is a very special Lagrangian submanifold of the dual group moduli space. So I won't define O pairs right now, but I will at the end of the lecture need the definition. So let's just say, for now, I'll just say the following. If you want to know, once you study BCC, you naturally want to know what's its dual. The answer was known by Beilinson and Drinfeld. And after actually struggling a lot, we eventually got a physics-based explanation of it. Or I should better say a four-dimensional gauge theory-based explanation. You could argue that the Beilinson-Drinfeld explanation was physics-based because all the ingredients they used were ingredients of two-dimensional conformal field theory. What Guyotto and I had here was a gauge theory-based explanation. Now to summarize, and I'm sorry there isn't time for a more detailed introduction, the main ideas in the gauge theory geometric Langlands correspondence are the following. First is electromagnetic duality of supersymmetric gauge theory in 4 dimensions between the group and the dual group. Twisting to make a dual pair of topological field theories. The dual theories have dual sets of line operators. Specializing, I forgot to write this, I think, but specializing to 4 manifolds, which is the product of a fixed 2 manifold times a variable 2 manifold. Then on one side of the duality, there's a distinguished brane BCC, establishing a map from A branes to D modules. And on the other side, one is studying B branes in the complex structure in which Higgs bundle moduli space parameterizes flat bundles. So these are sort of the main ideas, but I certainly didn't explain them adequately. And I left out a couple important points in this list, like specializing to a 4 manifold that's a product. But anyway, that's as much as we have time for today of a review of the gauge theory approach to geometric Langlands. Now, this story so far has involved deformation quantization, not quantization. But quantization is fundamentally not the same as deformation quantization. And the difference between them is extremely important. I try to not use the phrase quantization as a shorthand when I mean deformation quantization. But I have to admit that because the phrase deformation quantization has so many syllables, it's clumsy to avoid that shorthand sometimes. But because the difference between quantization and deformation quantization is so important, I'm going to spend a couple minutes to try to state that difference in a way that's so clear that hopefully there can't be confusion about it. I'm going to give the concrete example of a 2-sphere, x squared plus y squared plus z squared equals j squared, where x, y, and z are real, and j is also real. So this is just an ordinary real 2-sphere, viewed as a symplectic manifold with its usual rotation invariant symplectic form, which can be written this way, although that formula is not manifestly symplectic rotation invariant. The rotational invariant way to describe it is that it's the area form. The standard area form on a round sphere is the symplectic form that we're studying. In deformation quantization, you start with the commutative algebra of functions on the sphere. So you can think of those as polynomial functions of x, y, and z. Let's say complex valued polynomials in x, y, and z. And the problem of deformation quantization is to deform that commutative algebra to a non-commutative algebra, with the leading non-commutativity being given by the Poisson bracket. So in general, you ask for an family of associative algebras over C bracket H bar, or maybe C double bracket H bar. In other words, the difference is that in one case, H bar is a real or complex number. In the other case, it's a formal power series variable. But you want an actual or possibly only a formal deformation of the classical commutative algebra such that the leading departure from commutativity will agree with the Poisson bracket. In this particular case, we can just write down the answer, which is given by the SU2 Lie algebra. So this these rules, these relations, together with this relation, define an associative algebra. And that associative algebra answers the question of deformation quantization of this particular manifold. Now, in the usual language of physics, nothing's been quantized because we didn't quantize the parameter J. If you've studied your quantum mechanics, you know that in the real world, angular momentum is quantized. The possible values of angular momentum are h bar over 2 times an integer. And that quantization of the continuous parameters of classical mechanics is how the subject came to be called quantization. Quantization hasn't happened because we've constructed an algebra, but we haven't constructed a Hilbert space of quantum states that the algebra acts on. This algebra was defined for any value of J squared, and it's not quantization. It's deformation quantization. Quantization means finding a Hilbert space of the appropriate size that the algebra acts on. That does not exist for arbitrary J. To construct the Hilbert space, you have to quantize the parameter J, set it to preferred values at which the Hilbert space exists. Namely, if J is h bar over 2 times an integer, then this algebra has an irreducible unitary representation, which is the quantum Hilbert space. So when we constructed the Hilbert space, we have accomplished quantization, not deformation quantization. So what I've told you so far is that the A model, when we are studying the A model of a complex symplectic manifold viewed as a real symplectic manifold, the A model is related to deformation quantization. That was not quantization. We were constructing algebras, but we weren't quantizing the parameters and constructing appropriate Hilbert spaces. I hope I've made that sufficiently clear so that I can go on and we'll now discuss quantization as opposed to deformation quantization. But here, as I've remarked, the special values of J at which the Hilbert space exists are the ones that we see in the real world of electrons, atoms, molecules, and so on. And it's because of the last step that the subject is called quantization. Now, Gukov and I asked whether the A model in this general setup can describe quantization rather than just deformation quantization. In other words, I've told you how we can make the A model describe deformation quantization of the commutative ring of holomorphic functions. But can we make the A model describe quantization of something? The answer is yes, under certain conditions. Recall that in general, we're discussing a complex symplectic manifold Y, which in geometric Langlands is the moduli space of Higgs bundles, viewed as a real symplectic manifold with symplectic form M omega. Well, let's discuss Lagrangian A-branes, which means branes supported on a submanifold L that's Lagrangian for M omega. Well, in many of the examples that are important in geometric Langlands, L is actually a complex Lagrangian submanifold, meaning that it's Lagrangian for omega, not just for M omega. For example, if you take a skyscraper sheaf on the dual group side, supported on a point in the dual group moduli space, its dual is a Lagrangian brane supported on a fiber of the Hitchin fibration. A fiber of the Hitchin fibration is a complex Lagrangian submanifold. So this is an important example of an object in the A model of the Higgs bundle moduli space, where the Lagrangian is actually complex Lagrangian. The reason it happened is that a point in the dual group moduli space is hyperholomorphic, which leads to the dual being a complex Lagrangian submanifold. So in general, L is not required to be Lagrangian for omega, only for M omega, just as a coherent sheaf on the dual group moduli space is not required to be hyperholomorphic. So actually, the hyperholomorphic ones are highly non-generic. So most objects in geometric Langlands correspond to A-branes that are not supported on complex Lagrangian submanifolds, only on submanifolds for M that are Lagrangian for M omega. Now, Gukov and I considered the opposite case of an A-brane whose support is Lagrangian for M omega as it's required to be, but is symplectic for real omega. In other words, instead of assuming that real omega was 0 restricted to M, we consider the opposite case where real omega is non-degenerate when restricted to M. And we show that in this case, Hom from B to BCC represents a quantization of M with symplectic structure real omega. So this is a situation where we can make the A model produce something which is appropriate as a quantum state space. So for example, suppose Y is an affine variety. Then the holomorphic functions which are deformation quantized to get A, well, they're the holomorphic polynomials on Y, but they can be viewed as, okay, let Y be an affine variety that's a complexification of a real affine variety M. Then the real analytic functions on M have analytic continuations that are complex analytic functions on Y, which were deformation quantized to get this algebra. And this algebra acting on this state space means that certain real analytic functions on M have become operators on the state space. And there are enough of them to be a reasonable quantum deformed algebra of observables. So Hom from B to BCC is an A module that is a module for this, well, these real analytic functions on M that one can show has appropriate properties to be a quantization of M. So a formal argument actually reduces the description of H to the problem of quantizing M. Actually, I'm going to stop for a moment in case there are questions here.
Yeah, maybe, sorry, maybe just to say that if you want to ask a question, please raise your electronic hand and we'll try to put your question in the appropriate pause or break. Thank you.
Okay, I'm not seeing them now though, so I'm just going to go on at the moment. Now, I've omitted in this explanation a key point, which is that I defined a vector space of physical states.
Sorry, Edward, before you proceed, so I think there is actually a question.
Okay.
From Maxime. Mm-hmm.
Yeah.
Good.
Yeah, please go ahead. Ask a question, Maxime. We don't hear you. Oh, yeah, sorry, there is some confusion. Yeah, let's, Maxime? Well, I don't know.
We can't hear you.
No, oh, maybe you hear me now.
Oh, now we can hear you, yes.
Okay, yeah. So I have a very simple question. In mathematics, there are, when you consider as algebraic variety moduli space of flat connections, there are two algebraic structures, namely as bundles with flat connections, algebraic bundles with connection representation of fundamental group, and they're very different. And does physics prefer one of these algebraic structure? Is some way to speak about algebraic structures?
Well, that's an excellent question, which I've actually often been asked. I actually think that the duality applies to either one. Yeah. So, I believe they'll be so. Okay, what Maxime is saying is the following: on the B model side, in the two-dimensional description, roughly speaking, you have coherent sheaves on this complex manifold, but the complex manifold actually has two different algebraic structures. And, well, you can actually impose different, you see, in a compact situation, there would only be one answer for what's meant by the category of coherent sheaves. In a non-compact situation, there are different things you might mean by that category. And I'd expect that each plausible definition of the category would be dual to something reasonable on the A model side. So I'd really hope that there are good A model duals for both your questions. Well, suppose instead of asking the question on the B model side, we look at it on the A model side. Similarly, in the A model, in the mathematical theory, there are a number of slightly different things that people define as the A model of a non-compact variety. And it's probably all of the interesting ones haven't been defined. Okay, I gave you a slightly abstract answer, but I want to say one other thing, which is that what's actually studied usually in the mathematical theory is the category where you only allow polynomial growth on the fibers of the cotangent bundle, roughly. And I suspect that that condition is sort of dual to a similar condition on the A model side. Okay, so are there any other questions?
Yeah, at the moment we don't see any other questions. So yeah, let's go ahead.
I'll go on. Okay, so here on this slide, I defined a space of physical states under appropriate conditions.
I think there is a question from Daniel.
Okay, go ahead.
Yes, we discussed this already 12 years ago, especially with Gukov. We disagree that you need a Hilbert space, but we agree that if you want to have deformation quantization is quantization, provided you have some auxiliary conditions, like considering group elements and not only the algebra.
Well,
this is a whole discussion.
Oh yeah, I think we should maybe, thanks for the excellent comment, but I think maybe we should postpone it until the end. I think I explained clearly enough what I meant as quantization as opposed to deformation quantization.
Yes, but I disagree with the basic axiom that you need a Hilbert space. You need auxiliary conditions, not Hilbert space.
In any event, Gukov and I investigated the conditions under which he could define a Hilbert space, but I haven't defined it yet. So far, I only defined a space of physical states. Now, what structure is needed so this space of physical states is a Hilbert space, not just a vector space? So in general, if B1 and B2 are any two branes, there's a non-degenerate bilinear, not Hermitian pairing between Ham B1, B2 and Ham B2, B1. So to get a Hermitian inner product is the same as finding an antilinear map from one of these spaces to the other. So we showed that there is such an antilinear map, which I'll call theta sub tau, if there's an anti-holomorphic map tau from Y to Y, with M as a component of its fixed point set. I won't explain the definition of theta tau, but I'll explain why you should expect to need such a criterion. If holomorphic functions on Y act on H and H is a Hilbert space, one will have a notion of which holomorphic functions on Y are Hermitian, which in the classical limit would mean which functions are real. But the existence of such a tau gives a natural notion. A holomorphic function on Y is real if it's real when restricted to M. So the holomorphic functions that are real on M are the ones that were Hermitian with this definition. So if you're given tau, the Hermitian product on Ham from B1 to B2 is defined in this way, where theta tau is the antilinear pairing that's defined using, the antilinear mapping that's defined using tau, and the round bracket is the bilinear pairing of the A model. Now, in the generality I've stated, this pairing is always non-degenerate, but not always positive definite. For the more specific case relevant, okay, so this formula makes sense for a larger class of branes than we really want in the case of quantization. Roughly, they have to be tau invariant branes. For the case relevant to quantization, the best we can say is that the pairing is positive definite if you're sufficiently close to a classical limit. But not understanding that point better is a weak point of what I'm telling you. So in this approach to quantization, if you're given a real symplectic manifold M that you want to quantize, you have to find a complexification of M to a complex symplectic manifold Y with some appropriate properties, and then you can use the A model of Y to quantize M. That might be compared loosely to geometric quantization, which is the closest there's been to a systematic approach to quantization. In geometric quantization, to quantize M, you have to find a polarization of M, roughly a maximal set of Poisson commuting variables. And then given a polarization, geometric quantization gives a recipe for quantization. So here I've mentioned two recipes, geometric quantization and quantization by Branes. They can each give good results if there's a natural polarization in the first case, or natural choice of complexification in the second case for the problem at hand. So, and if there isn't a natural choice, then you're going to be out of luck. So a limitation of my paper with Gukov is that we didn't understand much about how to compare brane quantization to geometric quantization. Now, Gaiotto and I looked at this again in the last few months as background to understanding the work of Eddinghoff, Frankel, and Kazhdan that I mentioned at the beginning. At some level of precision, we've been able to compare the two approaches to quantization in the following sense. Well, the best you can hope for is that if n can be quantized both ways, then the two quantizations will agree more exactly, the best you can hope for is to have a criterion for when you can predict that the two quantizations agree, assuming m can be quantized both ways. So if m has a polarization p in the sense of geometric quantization and has a complexification y that's suitable for brane quantization, and if p has certain properties, then the two methods of quantization agree. So there isn't really time to explain the exact statements, but I just want to convey that we were able to compare the two methods of quantization, not always, but in a way that was useful for understanding the work of Eddinghoff, Frankel, and Kazhdan. Now, all this is by way of preparation to talk about the work of Eddinghoff, Frankel, and Kazhdan that I mentioned at the start. So they considered a Hilbert space H of L2 functions, or more accurately, half densities, on the moduli space of stable homomorphic G bundles. They constructed operators on the Hilbert space that are related to the usual constructions of geometric Langlands. And they formulated interesting duality theorems and conjectures concerning the action of these operators. I understand that in the p-adic case, some pieces of it have been, or similar things have been done by Kontsevich previously, but that is work I don't know much about. So I'm not going to state right now what their duality theorems and conjectures were. I'm going to proceed with the physical setup and we'll see what the statements might be. So in geometric quantization, we'd understand the L2 functions on the moduli space of bundles in terms of quantization of its cotangent bundle. And the cotangent bundle is birational to the Higgs bundle moduli space, which for an L2 theory is good enough. So you can say that the Hilbert space of Eddinghoff et al. Is what you get if you take the Higgs bundle moduli space with its real symplectic structure M omega and quantize it by geometric quantization using the fact that it's a cotangent bundle. So they studied this complex symplectic manifold viewed as a real symplectic manifold and quantized it in the sense of real ordinary quantization. Now, on the other hand, if we're going to get anywhere in terms of predictions from duality, we need to understand the quantization of this moduli space in terms of branes. For this, the first step is to pick a complexification of the Higgs bundle moduli space. Any complex manifold, viewed as a real manifold, has a canonical complexification. We simply take two copies of Y with opposite complex structure. The product of two copies of Y with opposite complex structure is a complex manifold that's naturally viewed as a complexification of Y. Because since we took opposite complex structure on the two copies, the involution, this should be Y hat, not U hat, the involution of Y hat that exchanges the two factors of Y is anti-holomorphic. Its fixed point set is the diagonal. So we've realized the diagonal as the fixed point set of an anti-holomorphic involution of a complex manifold. As I explained, the appropriate setting for quantizing something via Branes is to view that something as the fixed point set of a complex manifold with some good properties. So here, the complex manifold is just two copies of Y, and Y is embedded as the fixed point set of the anti-holomorphic involution that exchanges the two copies. Since the two complex structures on the two factors are opposite, we can take the symplectic form of the product to be half omega on one factor and half omega bar on the other factor. And then we pull that back to a complex symplectic form, omega hat on y hat. So the restriction of omega hat to the diagonal is real omega, which means, and in particular, the restriction of m omega vanishes. So, gosh, there should be hats here. Here and here, there should be hats. So the diagonal y is Lagrangian for the imaginary part of omega hat, but it's symplectic for the real part of omega hat. So this is the correct situation to quantize y by Branes. This is the appropriate situation in which quantization of y using a Lagrangian brane B supported on y makes sense. Moreover, the real polarization of y that leads to the Hilbert space studied by Eddinghoff et al. Has the appropriate properties that that Gato and I needed to be able to compare quantization by Branes to geometric quantization. That's important because I want to apply duality to brane quantization of y, but I want to know that what I'm applying it to is the same as the ordinary quantization of y as a cotangent bundle. So, well, to say it differently, this sentence means that the Hilbert space studied by Eddinghoff et al. Is the one that arises in brane quantization. So we can apply what we know about branes and duality to this Hilbert space. However, we have to ask what are the observables in brane quantization. Let's recall Hitchin's integrable system. The Higgs bundle moduli space has a Hitchin fibration from Higgs bundle moduli space to what I'll call B, which is just Cn for some n. The linear functions on B are Hitchin's commuting Hamiltonians. Classically, the global holomorphic functions on the Higgs bundle moduli space are just the pullbacks of functions on B. In other words, the algebra A0 of holomorphic functions on the moduli space is the algebra of polynomial functions in the Hitchin Hamiltonians. What are the quantum observables in brane quantization? Well, for brane quantization, we define the canonical coisotropic brane B hat CC of the product Y hat. It's just a product of canonical coisotropic branes on the two factors. So the algebra that acts will be a product A tensor A bar, where A is Hom on the first factor and B is Hom on the second factor. These are quantum deformed versions of A0 and A0 bar, the holomorphic and anti-holomorphic functions on Y. For the case of Higgs bundle moduli space, you can show that the quantum deformed rings are still commutative. In other words, Hitchin's classical Hamiltonians can be quantized to get commuting differential operators. That's due to Hitchin for SL2 and to Beilinson and Drinfeld in general. The four-dimensional gauge theory picture gives another explanation of the fact that the quantum deformed ring is commutative, similar to the explanation I gave of the fact that Hecke functors at distinct points commute. Now, so we want to understand the action of Hom from BCC to itself, which is A tensor A bar, on the Hilbert space, which is L2 of the moduli space of bundles. First of all, there's no mystery in the fact that A tensor A bar dogs act on this Hilbert space. It's just the statement that holomorphic and anti-holomorphic differential operators can act on functions on the moduli space. Holomorphic operators trivially commute with anti-holomorphic ones, and the algebras of holomorphic or anti-holomorphic differential operators are commutative separately because of the result I mentioned on the last page due to Hitchin and Beilinson and Drinfeld. So A tensor A bar acts as a commutative system on this moduli space. But what are the joint eigenvalues of Hitchin's Hamiltonians and their complex conjugates? To answer this question, we will apply duality. To apply duality to Hom from B to BCC hat, where BCC hat was the product of the two coisotropic branes, naively we need to understand the duals of the three branes involved. The canonical coisotropic brane, its cousin with opposite complex structure, and the brane supported on the diagonal. So as I explained before, BCC1 is the one that Bailenson and Drinfeld showed its dual is the structure sheaf of the variety of O pairs. An O pair is a flat bundle whose holomorphic structure obeys a certain condition that I'll state later. So that's the result of Bailenson and Drinfeld that I struggled with and eventually got to, and I got a reasonable answer from the physics point of view. BCC2 is the brane associated to deformation quantization of the ring of anti-holomorphic functions. So its dual is the structure sheaf of L O pair bar, the Lagrangian submanifold that parametrizes flat bundles, whose anti-holomorphic structure obeys an O pair condition. What about the brane supported on the diagonal? There's an unfolding trick that shows that this question has a trivial answer. So we quantized Y by considering two copies. So I've drawn a picture with two sheets representing the two copies of a theory with target Y. And the two copies are independent on the left boundary because the brane on the left boundary was a product of a brane for one copy and a brane for the other copy. But on the right boundary, the brane was supported on the diagonal, which means the two copies are glued together on the right boundary. So if I unfold it, I should just have a single copy of Y with opposite boundary conditions at the two ends and nothing in the middle. So in the unfolded version of the problem, there's just a single copy of the Higgs bundle moduli space, and the Hilbert space is Hom from one coisotropic brane to its sort of complex conjugated cousin. And we don't have to worry about this diagonal. We don't have two copies anymore in this description. So we just dualize the coisotropic brane and its cousin to get the variety of O pairs and its opposite. That means the varieties in the Higgs bundle moduli space that parameterize flat bundles whose holomorphic or anti-holomorphic structures are O pairs. So A becomes Hom from the variety of O pairs to itself, which is just the algebra of holomorphic functions on the variety of O pairs. And A bar becomes the opposite, the variety holomorphic functions on the variety of anti-holomorphic O pairs. So here are the dual pictures. We have a strip. In one picture, we have the coisotropic brane and its opposite. In the other picture, we have the variety of O pairs and its opposite. So the spectrum of A tensor A bar is Hom from the variety of O pairs with opposite complex structure to the variety of O pairs with ordinary complex structure. Now the two L's are Lagrangian branes, so their intersection is a Hom space in a version of Floer cohomology. So I wanted to elaborate a little on the statement that L op and L op bar are complex Lagrangian submanifolds in the same complex structure, but I'm a little bit worried about the time. Well, maybe I'll do it very quickly. So the G-dual description is by a B model of the Higgs bundle moduli space in which G-dual, the moduli space parameterizes flat G-dual bundles over C. The complex structure just comes from the fact that G-dual sub C is a complex Lie group. So for example, traces of holonomies are holomorphic functions in this complex structure, leading to Maxime's question from a few minutes ago. Maxime's question was whether this kind of holomorphic function is allowed. As a physicist, I'd say it's up to us what class of observables we want to study, and duality could be applied to either class. But for this present discussion, it makes sense to include this class. A flat bundle has both a holomorphic structure and an anti-holomorphic structure, both of which vary holomorphically. So in fact, there's a holomorphic map to two copies of the moduli space of G bundles, one on C and one on C bar, where C bar is C with opposite complex structure. And a flat bundle can be an O pair holomorphically if it obeys a Bailenson-Drinfeld condition, or anti-holomorphically if it obeys a dual Bailenson-Drinfeld condition. And either condition defines a complex subvariety, complex Lagrangian submanifold of the same moduli space. So by the method I explained before, using an anti-holomorphic involution tau, This Helm space carries a Hermitian inner product, which we expect to be positive definite, as it corresponds to the quantization of a cotangent bundle. The dual therefore carries a non-degenerate, the dual likewise carries a non-degenerate inner product, defined in a similar way using an anti-homomorphic involution of the dual group moduli space. The non-degenerate product can be defined for any B branes that are exchanged by tau dual. But for generic B branes, this will not be positive definite. Conditions that make it positive definite were formulated with a slightly different motivation by Eddinghoff et al., who showed that these conditions are satisfied for GL1 by a direct computation, but surprisingly non-trivial, and for SL2 by a theorem of faultings. So on the dual side, Helm from LAP bar to LAP comes from intersection points of these two Lagrangians. So it corresponds to it comes from a flat bundle E that's a pair both holomorphically and anti-holomorphically. The anti-holomorphic involution tau dual that's used to describe the Hermitian structure on the dual side will map E to the complex conjugate flat bundle E bar, which is also an O pair both holomorphically and anti-holomorphically. If E and E bar are not isomorphic, then they both correspond to null vectors of the Hermitian form, which in that case is not positive definite. But the duality predicts it should be positive definite. So we expect that, as conjectured by EFK and proved in some cases, E is always isomorphic to E bar. Thus, the claim is that the flat GC bundles that are O pairs both holomorphically and anti-holomorphically are actually real. That is, their structure group reduces to a real form of G. I don't know if it's always the split real form, but I imagine that's the case. Now, assuming the intersection points are all real in that sense, this Helm space is positive definite if and only if all the intersections are transverse, which is actually among the results / conjectures of EF and K. Note that if a flat bundle E is an O pair holomorphically and is also real, then it's also an O pair anti-holomorphically. Bundles with this property are what EF and K called real O pairs. So assuming the duality is true and the Hermitian form is positive definite, the joint spectrum of A and A bar corresponds to real O pairs. So to spell out more explicitly what that means, let me recall that according to Balanson and Drinfeld, an element X of this algebra has two interpretations. One, it's a holomorphic differential operator on the moduli space of bundles. And secondly, it corresponds to a holomorphic function on the variety of O pairs. Similarly, an element X prime of the conjugate algebra is an anti-holomorphic differential operator and corresponds to a holomorphic function fx prime on the variety of anti-holomorphic O pairs. So an intersection point of the two varieties determines a pair of eigenvalues for the differential operators x and x prime, namely the function corresponding to x evaluated at the intersection point, and likewise the function corresponding to x prime evaluated at the intersection point. So this is the proposal for the joint spectrum of Hitchens quantized Hamiltonians. And it's been, at least in some cases, partly justified, at least in some cases, by Eddinghoff, Frankel, and Kazdan. Eddinghoff et al. Also introduced Hecke operators as operators on the Hilbert space H that arises in quantization of the Higgs bundle moduli space as a real symplectic manifold. So I understand there's a periodic version that was discussed by Maxime, but I can't claim to know anything about that. I explained already that line operators of the four-dimensional theory can be used to define functors on the category of branes. And 't Hooft and Wilson line operators correspond to dual pairs of functors on the A and B model categories. The same line operators can be used to define operators in the ordinary sense of Hilbert space operators on the quantum Hilbert space. I've tried to explain this with the following picture. So in A, I show the old story of a line operator T as a functor on the category of branes. What I said before is that if you move T to the left, it transforms B to a new object in the category of branes. Now that I've drawn a two-sided picture, I can remark that you can also move T to the right and let it act on B prime instead, which I imagine is described algebraically as a duality between these functors. In B, I'm using the same line operator to make an operator from the Hilbert space to itself, where H is Hom from B prime to B for some branes B and B prime. You see, in this picture, a quantum state representing an element of Hom from B prime to B comes in at the bottom. It meets T and goes out at the top as a possibly different vector in the same state space. So in this, so here A was, in A, T is rather abstract from the standpoint of physicists. It's a functor on the category of branes. But in B, T is used, the same T is used to define simply an ordinary operator on a quantum state space. But my explanation in B was incomplete because I need to explain what's happening at the corners where T meets the brane B or B prime. And the point of picture C is to explain the answer to that question. See, by bending T upwards, well, we could eventually, if we want, bend it backward and make B prime. But locally, I've bent it upwards, and you can see that just what's happening on the left is a map, is an operation that goes from the object B to the object BT. So in other words, what is living at the corner is an element of Hom from B to TB. Because in the past, before this point, in other words, down here, we have the object B in the category of boundary conditions. But above it, you can imagine moving T all the way to the left, and we'd have a new object TB in the category of boundary conditions. So the corner is an element of Hom from B to TB. And I've said that here. And a similar argument shows that the corner on the right-hand side is an object beta in Hom from TB prime to B prime. So I explained before that line operators regarded as functors commute, but the same type of argument shows that line operators used as ordinary operators also commute. Because they live at different points in C, they can be moved up and down past each other in this picture without a singularity. So in this picture, two line operators are used to define ordinary operators on now a Hilbert space, not on a category, and they commute for the same reason as before. Since they live at different points in the two manifold that isn't drawn, they can be freely moved up and down past each other without singularity. A similar argument shows that the Hecke operators commute with the quantized version of Hitchin's holomorphic or anti-holomorphic Hamiltonians. So here again, a two-dimensional picture looks like there might be a problem in moving a Hamiltonian past a Hecke operator, but in 4 dimensions, there's no problem. Finally, we can ask what are the predictions of the duality for the eigenvalues of the Hecke operators. To answer this, we start on the dual side. We're going to find the eigenvalues of a Wilson operator in the A model side, and then the duality will predict that the eigenvalues of the Hecke operator on the automorphic side will be the same. Also, we'll find what kind of data is needed for the corners that will make the Wilson operator into an operator. Again, the duality predicts we need the same data on the dual side. Now, given a G-dual bundle E with connection over a product of two manifolds and a representation of the dual group, we can make an associated bundle E sub R, which mathematicians like to define this way, which also comes with a connection. And then what I'm calling WR of gamma for a path gamma is defined by parallel transport of the connection on ER along the path gamma. For the present application, we pick a point P in C, and we take 2 points A and B on the right and left boundaries. And we take a path in sigma times P that goes from A times P to B times P. We can just draw a horizontal straight line in the two-dimensional picture. It lives at a point in the hidden two manifold. So if ER comma A times P or B times P are the fibers of E sub R at these points, A times B or B times P. Then parallel transport defines for each connection a linear transformation WR of P from one fiber to the other. But I'd rather describe it more symmetrically and say that it defines an element in HOM from one fiber tensored with the dual of the other fiber into C. So R prime is the dual representation. So by replacing R to R prime, I replace this fiber by its dual. So WR of P at the moment is not a complex valued function. It's an element of the HOM from a vector space to C. A quantum operator is supposed to come from something that's a complex valued function of connections. So we need to turn this into a complex valued function of connections. So to do that, we will supply elements V in this space and W in this space, and then WR comma P applied to V tensor W will be a complex value, will be for each connection a complex number. In other words, it will be a complex valued function of connections, which we can quantize to get an operator. And that'll be an easy operator to diagonalize, as we'll see. To avoid unnecessary details, I'll only state the following for the case that the dual group is SL2, and that R is the two-dimensional representation, which means that R is also the same as R prime. There's a straightforward generalization to any group and representation. In this picture, the boundary condition at the right boundary is that the G-dual bundle restricted to E is an anti-holomorphic pair, which according to Balanson and Drinfeld means that there's a non-split exact sequence from K bar to the 1/2 to E sub R, where K bar is the canonical bundle of C bar. C bar is C with opposite complex structure. K bar to the 1/2 is a square root of it. Here we're picking a square root, but as EF and K noticed, this choice cancels out in a moment. So if we pick a vector V in K bar to the 1/2, we get a vector J bar of V in the fiber of E sub R. Similarly, on the left boundary, the boundary condition says that E is an anti-hom, is a holomorphic pair, implying that there's a non-split exact sequence. I left out, this goes to 0 on the right. So we pick W in KP to the 1/2, and that gives us J of W in this vector space. In other words, the corners we need in the picture are elements V of K bar to the 1/2 and W of K to the 1/2. Once they're picked, we act with the Wilson operator on J bar V tensored with J of W. And that gives the complex valued function of connections that we will interpret as a quantum operator. That step's trivial because in the B model, well, up to a nuance I'll state in a moment, you can assume that the connection is pulled back from C. And then the Wilson operator is just the natural dual pairing between these two bundles. So its value at a given real O pair is simply the pairing using the duality of the space between these two vectors. So it's convenient to write this formula in this way in terms of V and W, but it only depends on V tensor W in the tensor product of these two vector spaces. And that tensor product did not depend on the choice of a spin structure. So then the duality predicts that on the dual side, the definition of the 't Hooft operator as an operator requires corners in these spaces. That's true, as was shown by EF and K using an algebra geometric formula. And the duality predicts that the eigenvalues of the resulting operator are what we found on the dual side, namely this, for all possible real O pairs. Except that as a result of a recent lecture by Edward Frankel, I learned of a slight refinement. Because SL2 has a non-trivial center, plus or minus 1, when I said that parallel transport from left to right was trivial, it's actually only trivial up to an element of the center. And therefore, the eigenvalues are plus or minus what I said, with both signs occurring. So I'm sorry that I've rushed through, well, unfortunately, I probably rushed through both halves of the talk. But in summary, I tried to review the gauge theory formulation of geometric Langlands, why that's related to deformation quantization, how the ingredients involved can be associated to quantization, not just geometric quantization, and why this makes it possible to give a physics-based or gauge theory perspective on the work of Eddinghoff, Frankel, and Kazhdan, who have given an analytic version of the geometric Langlands correspondence. Thank you.
Thank you, Edward, for a very interesting talk. Please, questions or comments? I see that Marco has a question. Marco?
Hi, Edward. Thanks for the great talk. Can you hear me?
Yes.
Okay, I was just wondering about something a little bit more basic than the later part of your talk. So do you think that it is reasonable to include the holomorphic Lagrangian polarization of the coisotropic brane as part of the data of the object? Do you believe that maybe the definition of the brane should include that polarization?
No, but I think that complex polarizations are useful. So when I said that, unfortunately, there wasn't time to explain what Gauss and I were doing, but I said that under certain conditions, we gave a criterion to partially compare brane quantization to geometric quantization. We needed it in the lecture because Eddinghoff et al. Were doing geometric quantization, but we could only apply duality to brane quantization.
The reason that I ask this is that in every case, oh, sorry, go ahead.
What I was going to say was that to make the comparison, we needed the polarization of M to extend to what we call a homomorphic polarization of Y. Mm-hmm. So we used what I think you're asking about, which mm-hmm. is the fact that Y might have a complex polarization, but it wasn't part of the definition. We don't want it to be because Y might have different complex polarizations.
Yes.
And the non-trivial output of the theory is to predict under certain conditions that M with different polarization, the different quantizations of M are equivalent. The main drawback of geometric quantization to me is that there's no general theory of when quantization with different polarizations is equivalent.
Yes, absolutely.
Whenever you can say that, it usually leads to important results, very fascinating results.
I agree. So the reason that I asked the question is that in every case that I'm aware of where a homomorphism space between a coisotropic brane and some other brane has been computed, it's always been done using a polarization.
That doesn't shock me, but nevertheless, I don't want the definition of the coisotropic brane to depend on polarization, because then you're not able to claim that the results you get in different polarizations are equivalent. So I know quite a few examples where quantization in different polarizations is equivalent, and it can be explained by the fact that the definition of the coisotropic brane does not depend on the choice of a homomorphic polarization.
Okay, I have only one last question, then I promise I'll be quiet. So what do you think is the fundamental difficulty in defining HOMs between coisotropic branes from first principles? Why can't we get like a proper definition of this as we do in the Fukaya category?
It's very hard because what mathematicians view as a fundamental definition is pretty much close to what physicists call an answer. So since HOM from the coisotropic brane includes quantization and quite a lot of generality, in particular, you'd have to have an answer for quantization of M whenever it has the properties I used in my lecture, which admittedly I breezed through those properties a bit fast. That's a bit of a problem. But see, to me, there's something worse, which is that Poisson and Orlov explained what are rank 1 coisotropic branes. But higher rank coisotropic branes are extremely interesting and important, but we don't know what they are, except in very special cases, or at least I don't know what they are. I believe, well, you might know other examples, and I believe if David Garotto were on the call, he would possibly point to other examples. But offhand, the only examples I know of higher rank coisotropic branes that I can think of come from geometric Langlands, where you can the universal bundle evaluated at a point in some representation. That gives a higher rank coisotropic brane, but I don't know what general theory it's an example of. So, you see, physicists can live with this in the following sense. Okay, we can live with this in situations such as the case that Y has a complete hyperkähler metric, in which case we're confident that the quantum field theory really exists. That's the framework we're working in. We try to deduce its properties rather than looking for another definition. Mathematically, that definition isn't available. You look for another definition, which to a physicist would be an answer rather than a definition. And that can be hard work. There's some of it in geometric Langlands, actually, to tell you the truth. You see,
say that again.
There's some of that in geometric Langlands. The S duality of n equals 4 C rank Mills. is a simple unified statement, but if you try to spell it out in what mathematicians call a definition, it gets more and more complicated as you go into more and more detail.
Okay, thank you.
Okay, thank you. Ezra?
Yeah,
One last comment to the last question, right? Just want to say, as far as I know, we're still awaiting a paper that you lectured about a few months ago. So I'm looking forward to that because it was relevant. It is on more or less the things I was talking about, or the same general area. Go ahead, Ezra.
yeah, a similar direction, but a bit of a different emphasis. Instead of using polarizations, you can do geometric quantization using harmonic spinners. And I was wondering if there could be any potential role for that perspective here. So choosing a spin C structure, taking Dirac operator, and then doing the Hilbert space to be the harmonic spinners.
First of all, in my understanding, the right definition of geometric quantization uses a spin C structure, because what's traditionally called the pre-quantum line bundle is more accurately called a spin C structure. There's always a spin C structure in geometric quantization. But for the rest of your question, I believe it needs a polarization. In other words, unless you have an integrable complex structure, which gives a complex polarization, I don't think the Dirac you can study the Dirac operator, but I don't think it's convincingly related to quantization.
Well, I mean, it's just that in Wilfried Schmidt's work in the, so he was able to construct the discrete series exactly in the absence of polarizations by using harmonic spinners.
Are you sure there was no real or complex polarization in that work?
I'm not sure. I believe so, but I'm not sure.
I'd love to know, if it's true that there wasn't, I would love to know about that work.
All right, okay.
Maybe offline you can point me to what I should look at or give me any advice.
Okay.
Because the questions we're touching on at the end about what quantization means, when it's possible, when different methods of quantization are equivalent, well, has always fascinated me without satisfactory answers. My opinion is that that even partial answers have given extremely interesting results.
Yeah. Well, the work of Etienne Schmidt, basically, that's what I would suggest looking at. Yeah.
Okay, thanks a lot. Alejandro?
I wish Etienne was still alive because he'd explained it in a way I would have understood. But anyway, as it is, we'll have to make do. Go ahead. Go ahead with your question.
Hi. I wanted to ask you if you know of an example of the brane quantization scheme where the algebra that is the quantum algebra actually quantizes a non-symplectic Poisson bracket.
Well, the quick answer is no. So Gukov and I only formulated the case that the real part of omega was non-degenerate. You see, Kapustin, following Kapustin and Orlov, showed that the B model has a deformation that leads to a general Poisson structure, deformation quantization with a general Poisson structure. So to approach your question, having quantized Y with a general Poisson structure, is there something you'd want to call a real thing it acts on? Okay. Kapustin's work, Kapustin has shown, okay, the setup I've described here was more specific and is for complex Lagrangian submanifolds. But just for deformation quantization, Kapustin did exhibit how deformation quantization of the sheaf of holomorphic functions in a general Poisson, holomorphic Poisson structure comes into the B model. To my knowledge, nobody's asked the question whether what Gukov and I did has an analog in that context. And I wouldn't know what to say offhand. My guess is no, because my guess is no, but I can be wrong. If my guess was yes, I might have tried to do it. I don't know more than I said. I would start with what Poisson said about the B model and see if it inspired you to take some further step. But I don't know what that step should be. You see, deformation quantization works fine for general Poisson structures, but I might be too conservative. But to me, quantization as opposed to deformation quantization is for symplectic structures. Okay, I can't say much more. Well, one other thing I could tell you is the following. So, okay, well, suppose we have a complex symplectic manifold Y, so we do deformation quantization of Y. Then we could study a Lagrangian brane that's a complex Lagrangian brane. Gukov and I studied the opposite extreme, a Lagrangian brane for M omega that's symplectic for real omega. Of course, there's a whole world in between that is neither. No one's tried to say anything about that case, and I don't know if it would be in the spirit of your question. So therefore, I can't say if it would be. Maybe that would lead to something in the spirit of your question. I think one would want to have interesting examples to look at rather than being completely general. Maybe. I really don't know. I think I should stop there.
Okay, thank you. Any other questions or comments? I have a possibly naive question about the beginning of your talk. So you were speaking about those Wilson operators and Toft operators and how they commute in 4 dimensions.
Yes.
But are there some interesting higher dimensional defects that you can introduce into that theory? And then, of course, this commutativity probably wouldn't hold, right? If, for instance, a 1-dimensional defect probably would no longer commute with a 3-dimensional defect.
Yes. Defects of all dimensions can be introduced, and they're extremely interesting. And not everything's been done even at a basic level. So Gukov and I wrote a different paper where we introduced codimension 2 defects, or in other words, in 4 dimensions, defects supported on the 2 manifold. We called them surface operators. They're, in one way of using them, they're related to the what's called the ramified case of geometric Langlands. But just like in this lecture, you can use Hooft operators in different ways. Likewise, you could use surface operators in different ways. So there are other things that could be explored.
Sorry, surface operators would not commute. Is it the right intuition?
Probably. We didn't make any claim about commuting. Well, in the setup we had, the question didn't arise because the setup we studied was that the surface operator was supported at a point P and C times the whole 2 manifold. So since it was everywhere in the 2 manifold, the commutativity didn't arise. But I think you're correct. If you took a 1 manifold here times a 1 manifold in C, that would not be close to geometric Langlands, at least at first sight, because a real circle in C is hard to make sense of algebraically. Maybe you could make sense out of it if C has a real structure and the circle is a component that is real, but it's not immediately obvious. And anyway, how that picture would be related to geometric Langlands, but you're right, they wouldn't commute. We would have 2 vertical lines here that would live on different circles in the internal space. And since those circles intersect, we could not move them past each other. They wouldn't commute if we moved them past each other. There'd be a simple local answer in a sense. And you might be able to say something simple because they only intersect at a point, but they wouldn't simply commute. Then there are codimension 1 defects, which Gaiotto and I studied in a different paper as interfaces. Among other things, they lead to universal operations in geometric Langlands, and even to the universal kernel of geometric Langlands. But anyway, okay, that would be a different lecture.
Okay, thanks a lot.
Sure.
Maxime?
Yeah, I still have another question. Yeah, Edward, you somewhere in the early part of your talk, you said that this coisotropic brane is sheaf of differentials.
Yes.
Differential. It's algebra sheaf. Yeah. So did you use sheaf kind of consciously, or you repeat what mathematicians use?
Well, as a physicist, I would say the algebra.
Yeah. Yes. Yeah. Because it's this kind of because it's sheaf on not on symplectic manifold, sheaf only on the base of cotangent bundle. Yeah. It's kind of tricky story in a sense. Yeah.
Well, I don't know whether in perturbation theory it can be made into a sheaf on the total space.
Yeah.
If you want to have an actual deformation in your terminology, it's only a sheaf on the base space.
Yeah.
Well, okay, I actually regard your question as pointing to a weak point in all the work I've done by me and other physicists on this. So in physics, it's not that natural to sheafify the quasitropic brane, and most branes can't really be sheafified in the A model. But BCC can be partially sheafified in the way you say, and that's important in making some arguments. But since it's not ultra-natural physically to do that, I would like to find a way to avoid it. But that hasn't materialized. Anyway, I agree with your statements. I was cutting a lot of corners. Well, I rushed too much, I'm afraid, and tried to explain too much in too little time, but I was trying to cut some corners to save time.
Okay, thank you.
Sure.
Thank you. Well, we'll soon be approaching an end. Marco, more questions? You need to unmute yourself, or
just a follow-up on the last question. So do you believe that when dealing with these coisotropic branes, that there's a fundamental reason why you would not have instanton-like behavior?
Well, you and others keep asking questions that involve different ones of my papers or else papers written by my co-authors in some cases. So you're getting to one of my favorite topics, which has to do with analytic continuation of Chern-Simons theory and also Covenant homology. So what physicists understood originally about instantons and the coisotropic brane wasn't completely correct. Mm-hmm. And the whole story is fascinating, but it's impossible to properly explain it now. But the full story gives a different perspective on the role of quantization and deformation quantization in relation to the coisotropic brane. And, well,
where could I look for more information about what you just said?
Well, you see, I worked on, I wrote a paper called A New Look at the Path Integral of Quantum Mechanics.
Of course, yes, I know this.
Right there.
Okay.
And there's also my work on Covenant homology. And also, you see, there's a paper called Analytic Continuation of Chern-Simons theory.
This one I know, yes. But I didn't realize they were related to this.
They are, yes. So the question, okay. Your question, let me rephrase your question for you. In the A model, you're summing over pseudo-holomorphic maps. And then you ask me, what's the analog when BCC is in the game of the sum over pseudo-holomorphic maps?
Yes.
What's the boundary condition on the pseudo-holomorphic maps? Roughly. That was basically your question. You didn't spell
absolutely,
that.
Yes.
Now, the answer, I think, is incredibly fascinating. The answer is that there's no boundary condition. You simply integrate over the space of all pseudo-holomorphic maps. So you might have a Riemann surface with several boundaries. If some of them are Lagrangian branes, you have conventional boundary conditions there. But if others are pseudo-holomorphic maps, if others are rank 1 coisotropic branes, then where there's a rank 1 coisotropic brane, there's no boundary condition. Instead, there's a function that you need to include in the integral over the space of pseudo-holomorphic maps. And that function is the exponential of the action in analytic continuation of the action in quantization. Okay, there isn't quite time for a proper explanation now, but you need that function because otherwise the infinite dimensional integral wouldn't make sense. Mm. So it's an integral. Your question leads to an infinite dimensional integral, which is an analytically continued version of the path Feynman, its original path integral of quantum mechanics.
Okay.
So I realize I'm giving an answer that might slightly scandalize a mathematician, but to cheer you up slightly, the original Feynman integral in the conventional case of quantum mechanics is somewhat rigorous. The Euclidean version is completely rigorous.
Yeah.
And I think there probably are people who would claim that the Lorentz signature version makes some mathematical sense. Mm-hmm. I can't make any promises about how hard it is to make a mathematical theory here. But the answer to your question is that there's no boundary condition, there's just a function. And that was not originally understood. And therefore, some assertions in the original papers are not completely correct. Including
I agree with that, but I didn't know that there was a potential replacement for those errors. That's good.
Yeah.
Okay, thank you.
Replacement that makes it much more interesting. But also tells us how tricky these quasitropic branes are going to be.
right. Any more questions or comments? If not, let's thank Edward again for his wonderful talk.
Thank you for the invitation.
And now it is clear from the discussion that you will have to come again to Global Poisson and tell us more stuff, right? So thank you again. Thank you, everybody. So next week we'll have Chen Chang-Zhu speaking at Global Poisson. So thank you all, and see you next time.
Okay, thank you again.
Thank you all.